My name is Dennis Speed, and I want to welcome you on behalf of the Schiller Institute to panel 2 of our conference, U.S. China Cooperation on the Belt and Road Initiative and the Corresponding Ideas in Chinese and Western Philosophy. There are many things that could be said about the character of the topic, but both because we're starting a bit late and also because it will become eminently clear, we're going to just introduce our first speaker and go right into it. So the first speaker for this afternoon's panel is Jason Ross, Editor-in-Chief, 21st Century Science and Technology, and co-author of The New Silk Road Becomes the World Land Bridge.
Can we get the projector turned on? Okay, well, I'll go ahead and get started. So it's very good to be here. I'm glad to see so many people in the audience. And I think that we've heard really tremendous presentations this morning on what the Belt and Road Initiative can mean for the world, what the World Land Bridge can mean as a new standard of relations among nations and as a new basis for economics. I think that one of the things that we heard was about how geopolitics is being replaced by the Belt and Road Initiative, a new way of relating among nations. Geopolitics, the British Empire, this explains why, for example, the United States did not join the AIIB. It does not explain, in itself, why the United States let its infrastructure completely decay. So for that, I want to take a look at what new thoughts about economics are required by the Belt and Road Initiative. So if we, can we get this on here? Okay. If we look overall at the value of infrastructure is what I want to focus on today, because there's aspects of infrastructure that make it different from anything else in the economy, and wrong economic thinking about it prevents financing and prevents it from being built and holds us back from reaping all of the benefits that we could from investments in these sorts of projects. If we look at the human species as a whole, what characterizes us is the fact that over historical time, we have become a new species repeatedly. If we were looked at from the standpoint of biology, you would say that the human species has been supplanted and transformed into a new species, a new genus, a new family, many times in our history. We've seen this in the changing relationship that we have to our environment. So we've seen it in the changing number of people that can exist on the planet. This is a chart of human population over the past 10,000 years. No animal species willfully changes the number of its species that can live on the planet. We do that. How do we do that? We do it in what makes us human, which if we look back to the Greek creation story of the human species, to the story of Prometheus, we're told a tale of how the human species was created. That before Prometheus, we had bodies that were human, but we didn't have minds. We didn't use fire. Prometheus, in giving fire to mankind, and number, and poetry, and astronomy, and the calendar, and all of the arts, and metallurgy, and medicine, and sailing ships, and the use of animals. By giving knowledge to mankind, we became a new species on this planet. And that's the basis of our transformation in our living standards. Here you see a chart of life expectancies over time. The red line is life expectancies for different nations in 1800, where you can see even the nation with the estimated highest life expectancy, Belgium, the life expectancy was only 40 years in 1800. Think of what the average age of a person in a society like that would be. How advanced could such a society become if this is the maximum age people are reaching? You've seen the tremendous increase. We see what had been reached by 1950, and now today, 2012 and beyond, every nation in the world has a life expectancy that's greater than that of Belgium, which had the highest 200 years ago. That's something to be very happy about. and proud of, and reflects something that's absolutely different about our species from any other sort of life. So, what is infrastructure? If we think about our environment, think about the word environment for a moment. We use it in many contexts. Sometimes we mean specifically things like the air and the water around us. Sometimes it has a more general meaning, like the ambiance. What's the environment in a social situation? What's the environment like in a restaurant, for example? But our environment, the world that surrounds us, is increasingly one that we create. The resources that we use, unlike animals, are not ones that we find around us. An animal looks for plants to eat. An animal looks for plants to eat. A plant hopes some sunshine will land on it, right? These are just things that are around it. It doesn't create them, it uses them. For us, the synthetic environment that we create for ourselves, that is our infrastructure. And by mediating our discoveries that we have made, the science that we know, the technologies that we're capable of, by implementing them as a platform of infrastructure, we set ourselves up for a certain level of civilization, of economic potential. I'm going to run through very quickly 3 ways that this happens: in power, in materials, and in space and time. If we look at a chart of power use in the United States per capita over the history of our nation, we see both that power use overall has increased per person, and that the source of that power has changed from wood to coal, then increasingly to oil, natural gas. Fission never really made it off the ground. So more power and of a different kind. We can do something with oil that we can't do with wood. You are never going to build a car that operates on wood chips. Impossible. You can have a car that operates on oil. You're not going to have an airplane that someone is shoveling charcoal into a burner on it. Never will happen. It's something that we can do with oil. And then think about what we can do with electricity. More on that in a moment. Take a look at this chart. On the x-axis, we have electricity use per capita. This is for all the nations of the world, compared to per capita GDP. You can't have a high standard of living, even as measured in GDP, which is imperfect, without electricity. Energy, power, this is required for a high standard of living. What sources will be able to provide 5 times the world's current power use? For the world as a whole, per capita, to use as much energy as somebody in the United States per capita, we need 5 times as much energy. What will provide 5 times the current total energy on the planet? What power source is capable of doing that? And here you can see the uneven development currently, as exhibited in this very clear marker of power, light at night. Okay. So, one other thing on that. In terms of the way that we use power, take, for example, uranium. Now, uranium used in a nuclear power plant has a tremendous amount of power in a very, very tiny amount of fuel. Uranium could be burned. You could burn uranium if you wanted to. So you could take uranium and put it in a coal power plant. You could throw it in, burn the uranium, boil water, create steam, and run a turbine. Does anybody have an idea of how much less power you get from uranium if you treat it as a chemical compared to a nuclear fuel? About 100,000 times is the difference. So there's a limit for all chemical fuels. The power in the electric bonds that combine the atoms in a molecule, the power that's just potential in that kind of physical relationship is less than that in the nucleus by a factor of 100,000. Tremendous difference. Think about the materials that we use. On the next slide here. If we consider the materials that we have, Okay. Well, the materials that we use that on a regular basis, these have transformed throughout human civilization as well. Things that we take for granted or use on a daily basis, like aluminum, are possible only in an economy that has electricity. Without electricity, aluminum is very hard to produce, and bauxite is really not a resource. It's not commercially viable to produce aluminum from it without electricity. The plastics that we use, I mean, this is the other big use of oil. Besides airplanes, which I can't imagine running on a battery, the other necessary use of petroleum is plastic. But if you look at our relationship to material after material, to steel, to iron, to our production of nitrogen, artificial nitrogen fertilizer, a technology that by itself has increased the potential population of the planet by 25, 30%. Our environment is one that we create, and the resources that are around us are ones that we create. We create a resource. Discovering how to turn a rock into a metal, we have just now created a resource where one did not exist before. If you look at the change in how these are used, the amount of steel that we use, the amount of coal that we use, the production of rare earth elements. You know, people say that the use of resources like oil has fueled much of the conflict in the world, people trying to control the use of this precious resource. Well, what about rare earths? These weren't even considered a resource 50 years ago. Now they're a very major one. We made it so. Chromium, nitrogen, aluminum, steel. Okay. We also transform our physical environment in the sense of the space that's available to us economically. If you look at the distance that you could travel from New York over a certain period of time in 1800, where for this line, for example, this represents the limit of 2 weeks traveling from New York. By 1830, this is the line of the extent of 2 weeks travel from New York. It wasn't because faster cars were produced, it's because we transformed and created a synthetic environment for ourselves. We built canals, we built roads, we transformed our environment. By 1857, 2 weeks gets you all the way out here. We have rail lines now in the eastern part of the United States. And by 1930, you could reach anywhere in the country in less than half a week. So if we try to understand as economists the value of this type of infrastructure, we really miss the point if we only look at a business by business standpoint and try to estimate how much will a certain business benefit from reduced freight costs or reduced shipping times. What we have to take into account is the fact that an entirely new type of economic production is now possible. Now you can produce intermediate goods and ship them elsewhere. That kind of connectivity in industry is possible. The ability to move resources around, to site production in different locations. You've transformed how useful land is in all the areas along which this development corridor extends. So those are three ways that we've transformed and created an environment, which we can call infrastructure. For the future, the big three things, I think, are one, the development of fusion power, which will transform our relationship to nature in a way that's like the development of the steam engine, in terms of how huge the difference will be, where we can produce great quantities of power. We could, as this gets to the second point, desalinate ocean water, have a better control over our water systems on the planet, and totally transform our relationship to materials. With fusion, we would no longer need coal to produce metals, as we do today, for chemical reasons. I'd like to now discuss three problems that economists have in understanding the value of infrastructure, and then lay out four techniques for successful economic policy. Okay. So the first problem with the value of infrastructure and science is that the payback is not commensurable with the expense. To a monetarist, the way that economics is generally taught now, if you spend money and you make money, the return is some percentage of the cost. If you gamble on E-Trade and you make money, you spent money and you made money. It's like playing poker or anything else. It's not the case when you're investing in a new platform of infrastructure, where if you build out electricity lines across a nation, and now all of the economy can benefit from the use of electrical production, well, the payback is not a multiple of the cost. You have an incommensurable economy as a whole. How do you measure the value of that? Not purely in dollars, it misses it. How about in potential lifespan? How about in potential population? Much better measures. The second problem is that the value of an infrastructure platform or of a scientific discovery cannot be localized or expressed as the sum of localized bits of value added. That transcontinental railroad system as a whole had a value that can't be localized. The discovery of a scientific principle, Lisa Meitner's hypothesis that uranium was not decaying, but was actually fissioning or breaking up into large pieces. That idea of hers, which was right, well, that's the basis of fission power. That one idea transforms the entire human species instantly. As a whole, we are a different species based on an idea created by one person. Not localizable, right? And the third problem with infrastructure, when economists try to account for it, is that the return is indirect. If you build a dam and prevent flooding, well, maybe you don't make money directly from having done that, but clearly it has a value. Something that Rafael Correa pointed out in Ecuador recently with the massive flooding that had caused a great deal of devastation in Peru and Colombia, but Ecuador got by reasonably well because they had invested in water management infrastructure. And Correa said, bankers make the mistake of looking for a return. And that's fine sometimes for a private venture, but it's not right for the state as a whole. So if you think about things like public roadways, local roadways, these are things that don't create a direct return the way that rebuilding an airport terminal would, where a public-private partnership might indeed invest the money in rebuilding LaGuardia partially, but you're not going to get a PPP to take on a huge project like building up a transportation network to the Bering Strait. The return is too long-term and indirect. And so it's a problem to think that you have to be able to attract private finance. We need mechanisms appropriate for the nation. And those mechanisms are different than what a private enterprise would do. So let's take a look at these four mechanisms here, these four principles, in order to make all of this a reality. So Lyndon LaRouche, the economist, put forward four principles to make a recovery possible. The first one is Glass-Steagall. Now, many economists think that the way you create demand or create growth in an economy, if it's sluggish, is you lower interest rates and just make more money available. Trillions of dollars in loans and loan guarantees have been made available to Wall Street. And that money, those loans, are basically just sitting in the Federal Reserve. They don't go anywhere. They never leave the banking sector. Currently, in the United States, a great deal more of our GDP is attributed to finance than to manufacturing, for example. So money is just staying in the financial sector. With Glass-Steagall, we can force banks to get back into lending again. Investment banks can do what they want, but a commercial bank, the only way it's going to make any profit is by lending, which is what banks are supposed to do. As a matter of fact, we need a national bank in order to take advantage of opportunities for building infrastructure that don't create a direct return. We need a mechanism where an indirect payback is suitable for capturing the value created by building a new infrastructure platform, something that a national bank will allow us to do. And as we direct credit to enterprises and ventures and infrastructure and economic platforms, the metric is not a monetary one, it's a technological one. Are we increasing the energy flux density of the economy as a whole? Are we improving the amount of power available per capita? Are we improving the quality of power available per capita? Think about the need to expand our control over space, for example. You can build as many windmills as you want all over the planet. They will not get a rocket off the ground. Developing nuclear rockets, well, that gives us a whole new potential to redirect an asteroid coming our way, to have a greater control over space, etc. So the metric's not monetary, it's technological. And last, we need a crash program to develop fusion power as the next platform of power as a whole for the human species. With this, our ability to control materials, to control water, to control power, to create artificial fuels. We can create methanol, for example, instead of gasoline. We can save our petroleum for use in plastics where it's irreplaceable. And instead of burning it, we can use it to make things, plastics. We no longer cut down trees on a mass scale in the United States for power. We save our wood for furniture, which you're not going to build out of coal. So I would just say that we should really remove any problems, any inhibitions isn't the right word. There's a lot of very wrong economic thinking that we need to throw aside. The whole monetarist idea of economics, that everything can be understood in terms of individual bits of profit that are added up, as opposed to looking at a platform that provides an incommensurable value to what came before. That kind of economic thinking has to be rejected, because if we stick with it, we will never be able to finance the kinds of projects that we need in the United States. If Trump says we need $1 trillion, the American Society of Civil Engineers says we need $4 trillion, if Chinese experts say $8 trillion, if an engineer at a conference I was at on Friday says $10 trillion, well, where is all of that going to come from? It's not going to be purely by attracting private investments. We need mechanisms that reflect the real value, the indirect value, and the incommensurable value of infrastructure as a platform on which the entire economy rests. And we need to invest dramatically in the scientific breakthroughs that will make that next level of platform possible, such as primarily research on fusion power. Thank you.